Hello, everybody. Just a few words to introduce myself. I'm Stefano Di Paola, and CTO at Mandate Security, which is an application security company based in Italy. I'm one of the founders. I just manage of the research at Mandate Security, and I'm the director of research and development at OWASP, the Italian chapter. And my security research is about flash security. I'm the author of Swift Intruder. I do web stuff and web security stuff. My weblog is ysec.it.
I'm Kuza55. More or less, I'm just some random hacker. I like breaking things. I also work at an information security consultancy called SIFT. We do a bunch of app testing mostly, though we do some risk stuff as well. That's pretty much me. So today what we wanted to talk about were some DOM-based XSS stuff, which sort of has been looked at a bit in web app circles in like 1 or 2 papers, and really look into how browsers implement JavaScript and how they implement access controls and similar things, and what kind of trickery we can perform there. Also, we're going to talk a little bit about Google Gears. We did this presentation before last month at RuxCon down in Australia. Since then, Google have fixed some things, but we still think letting you know about what was there might be interesting. And we'll also show how typical, like XSS bugs in specific places in browsers can actually get you code execution. So, DOM-based XSS was sort of discovered in like 2005, resumed in 2005. It's essentially where you have JavaScript on a page which does some kind of unsafe operations. For example, if it got some data out of the URL and decided it's going to execute that as JavaScript, there's no typical XSS bug where things are being injected onto the page, but you're still able to execute JavaScript because you can control where the URL is. So the paper that Amit wrote talked about some kind of the basic inputs and basic sinks for DOM-based XSS. It talked about like what objects in JavaScript an attacker can control and what sinks in JavaScript it would be useful for an attacker to control input to. It didn't really talk about control flow at all. It pretty much assumed that control flow worked exactly as the language specified, and that the same origin policy was enforced properly for everything. We'll talk about that a little bit later. There was one blog post this year by Ori Segal from Watchfire where he talked about how if JavaScript objects are referenced in such a way that they're, say, referencing objects of parent frames that they think will exist, we can construct HTML files in such a way that the objects they're accessing don't cause a security exception. Go to that URL to read about that. That's not really what we wanted to talk about. Just to give some background, in the original paper, the Amit Klein talked about how the attacker can control things such as the URL in JavaScript, which is the first 3, the referrer, and the location. It was pretty much assumed that that's where you're going to get all your input from, and then if it goes to one of these sinks where it either writes attacker-controlled input into raw HTML or modifies the DOM in such a way that causes JavaScript execution, for example, via JavaScript URIs in forms or by simply executing JavaScript, or, of course, replacing the URL, or a bunch of other, essentially, actions that could possibly result in script execution. So if you have input coming from one of the sinks, which was essentially the URL or the referrer, and it was put unsanitized, from those inputs going to those sinks unsanitized, then you had a DOM-based XSS vulnerability. The problem here that I see is that all of those sinks focused on direct script execution. it's kind of like auditing, say, some PHP code and looking only for eval bugs where you can execute PHP code. There's a bunch of other things that you'd want to do. For example, on the server side, you'd want to be able to read files or inject in SQL and similar things. On the client side, there's also similar objects you want to access because there's no point in executing JavaScript unless that actually gets you something. So we want to be able to look at JavaScript code and look at if the attacker can force that code to modify or abuse some kind of sensitive objects, such as HTML elements or DOM elements, or leak or edit cookies, or perform some kind of client-side directory traversal attacks, and these kind of things. So, in the original paper, the HTML link that was pretty much the only one presented was the form action attribute, or like a link action attribute. If you can inject a JavaScript URI into one of those, and the user either submits the form or clicks the link, then the user's navigated to the JavaScript URI and the JavaScript executes. However, there's a bunch of other HTML tags that lead to essentially just completely unfiltered script execution. This has been studied fairly in depth by people looking into standard XSS bugs and all the different kinds of tags that lead to script execution. For example, JavaScript URIs and image tags, or being able to control the locations that Flash files are loaded from, and all these other kind of things. We need to start auditing like JavaScript for the ability to edit these kind of special objects and special attributes, rather than just looking for straight injection type things that earlier papers looked at. Yeah, so of course there's injections to CSS and other things. But essentially anywhere that you'd typically, any kind of tag that you'd use for a typical XSS attack is a tag that you need to look at as a sink for a DOM-based XSS. So, yeah. And then on top of that, you have the more non-standard type of XSS things that will work in your reflected XSS issue, but which you again people aren't really auditing for in DOM-based XSS bugs. For example, if you have a link such as the one there, which isn't all too common but sometimes happens, those kind of links actually also don't just execute the JavaScript, but they also write the result of that to the page. So, for example, in this case, if someone clicked on that link, then the string user underscore input would be written to the page as HTML. But this is really all more or less old stuff. We need to also think about like the kind of sensitive objects that are in there. CSS is an interesting example because at the moment we can jump from CSS into JavaScript in a lot of cases, but browser manufacturers are doing their best to shut this down. However, Stefano and Sir Darkat have discovered that in the latest CSS spec, or the HTML spec, being able to inject plain CSS, which doesn't execute any kind of JavaScript, is still dangerous because the CSS in the latest drafts can actually read values from the page and leak them offsite. We'll talk about this a bit later as well and do some demos, I think. Yeah. Okay. Other things that are usually considered like hard to do, such as spoofing the referrer. It's usually possible to strip the referrer header from HTTP requests, but being able to spoof it and control where it comes from is usually considered difficult and a bug and eventually gets patched. But if you have the ability to control the location of an image tag, either through straight XSS or more commonly through DOM-based XSS, where JavaScript simply edits the location of an image tag, then you can spoof the referrer of a request, or you can leak the current location in the referrer to your site, or even control the user interface, which, while usually derided as irrelevant, does help you with other attacks. Of course, yeah, typical JavaScript injections into links also work, as we mentioned before. But being able to inject links by themselves, even if they don't actually lead to JavaScript execution, still gets you something, gets you a link on the page which does actually have the referrer of the same domain. This is useful, for example, to bypass IE8's XSS filter, because that uses a same domain check to check whether it should be filtering requests or not. So if you inject a link onto a page and then through some method entice the user to click on that by some kind of either UI redressing attack or just some social engineering, then the IE XSS filter will be pretty much bypassed. And of course, injections into input tags are useful when you're trying to do some kind of like clickjacking style attack where you're enticing the user to click on a button to bypass CSRF protections. You need to be able to fill in input forms, and sometimes you can do this from the JavaScript that's embedded on the page. Yeah. And when you look at some of the JavaScript code out on the internet, a lot of it ends up being packed in such a way that it takes up much less space. Often this means that things are referenced using array notation. So, for example, you'll have like document, then open square bracket, some variable, close square bracket. If you control the contents of that variable, then you can obviously control where something is being assigned or where data is being accessed from. So, for example, if you were able to control the index of a read from the document object, you'd be able to set that index to cookie and then potentially leak those offside if there's if the sum var was used improperly. And of course, it goes the other way around. If you set, say, user input to location, you somewhat control sum var, then you'll also be able to set like the location of it, and which will lead to script execution. This is particularly useful not just for DOM-based XSS bugs, but for typical straight injections, like in reflective XSS attacks, where you need to bypass some kind of IDS. An IDS can only know about the objects that exist by default in the browser. If you modify some kind of variable that's sensitive to a JavaScript application, such as like the index it uses, you can easily modify the control flow of the JavaScript, and then it's pretty easy to lead to some kind of script execution, and IDSs really can't pick up on this. So, yeah. A quick detail about the IE8 XSS filter. As I said before, it only filters things cross-domain, but it took the bold move of trying to stop injections into straight JavaScript. It works to stop direct script execution in JavaScript, but using our knowledge of like the sensitive kind of objects that are in JavaScript, we can easily, for example, leak what's in the cookie object or change some variables and these kind of things to change the control flow, which will lead us to DOM-based XSS bugs, which we can later exploit. Yep. So, some new things we wanted to talk about. The document.cookie usually isn't really considered a sync because reading and writing cookies isn't considered sensitive for some reason. So writing cookies isn't considered sensitive. However, there were some good papers a while ago about how being able to set a user's session will lead to session fixation attacks where you don't need to leak a user's session identifier, but can simply control it and then have them authenticate to it. With document.cookie, it actually passes any kind of input that you set to it. So if you set document.cookie to equal A equals B, then a new line, then C equals D, two separate cookies, A and C, will be set with the values B and D respectively. On top of that, when we're trying to, when we're writing XSS payloads, we often use the XML HTTP request object to make requests to the site to get like CSRF tokens or perform actions and these kind of things. While this kind of interaction is usually not possible by DOM-based XSS attacks, it is possible to find injections into things like URLs. So if the app uses these like nice pretty URLs where things are separated by slashes so that search engines can find them, if you can control one of the parameters, you can perform client-side directory traversal attacks. And often if the site is using some kind of referrer checking or is using global tokens where a token for one action will be valid for another, then this will let you either perform actions, or perform actions on the site that are normally considered CSRF protected. Yeah. Of course, there are other sensitive objects inside the JavaScript, such as document.temp